Okay, and you see the ground state of a deuteron is consist of these two parts. These two states are present in the ground state of a deuteron, and here we are neglecting only this 3D1 part. Why? Because its contribution is 4%. Okay. Okay. Now coming to 87 number question, it is given that if ED, that is the binding energy of deuteron in the ground state, B is the range of the potential, V naught is the depth of the rectangular potential well, and kappa 1 is a capital M by S square, V naught minus ED. Then the transcendental equation for matching the ground state solution of deuteron at the boundary. Okay. So how can you find? First we have to find the wave function in different region. Okay. You see, first of all, it is given that we have to take the rectangular potential well. Okay. It is mentioned that we have to take the rectangular potential well. Okay. So if it is mentioned any kinds of potential well, like for example, short tooth potential, or for example square well potential, or harmonic potential, or wood section potential, then according to that potential we have to solve the coordinate equation. But for the simplicity, it is given that the rectangular potential well. Okay, so we have to take that potential well to solve the coordinate equation. So okay, so how can you solve? Let's see the solution. You see, but remember that this coordinate equation can be applicable only for single particle system. But here the deuteron is a two body problem. It has one proton and one neutron, so it is a two body problem. So what you have to find to convert it to single body? You have to make the reduced mass of this system. Okay, so if you take the reduced mass, then it will become a single body, because now we are solving this question in the center mass problem. Okay, so that's why we have taken the reduced mass. Okay, so mu is the reduced mass and it is equal to m by 2. Okay, as we have compared that, we have assumed that the proton mass and the neutron mass, they are more or less equal. Okay, so to solve the Schrodinger equation, so for that we have to take the time independent Schrodinger equation. Okay, this is the time independent Schrodinger equation, because there is no time term, and it is a this energy is not changing with time. Okay, so this is the Schrodinger equation. This potential here is the depth of that potential. Here you see in the question it is given that the depth of the question potential is V naught. Okay, okay, so what you have to find? Let's make some arrangement. Okay, you see how we are proceeding. You see, we are just arranging to find the wave function. There are two main regions. So for those two regions, we have to find the wave function. Okay, then we have to take the ratio to get the desired solution, that is the transcendental equation in the boundary, as mentioned in the question. Okay, you see how it is proceeding. You see, I am not talking each bit. You see just okay. Okay, now in the place of mu we put m by 2, because the reduced mass. Okay, so if you put, then you will get this. Okay, now it's time to put the value of depth of the potential as well as the binding energy of the deuteron. Okay, this energy is the binding energy of the deuteron. Okay, now in the place of here you put minus V naught. Okay, this potential is attractive, na? That's why this negative sign is coming here. Okay, so there are two regions. This is the rectangular potential well. This is the potential here, and this is the radius. This point is 0, and this is the range B. Okay, this point is B. Okay, and I am taking here R naught. You just put B. This R naught and B are same. Okay, so below B, this point B, the potential value is minus V naught. That means this depth is minus V naught. Okay, but after R greater than B, that means up to this, from this point to onwards infinity, it is getting 0. You see, it is 0. So that's why the potential becomes 0. And this is the attractive potential, that's why the minus sign is coming here. Okay, now as the deuteron is only, there is only bound state, only one bound state, and that is because it is loosely bound. Okay, so it has only one bound state, and that is almost, you can see, if you take the energy, that is the binding energy is of deuteron is almost, you can say, 2.225, I think, mega electron volt. But this depth, okay, this depth v naught, if you calculate actually, you get in the range of 52 or 40 mega electron volt, or you can say 36, I think 36 mega electron volt. Okay, so compared to that depth, your energy, that is the energy of a deuteron is very low. Okay, and it will be in the just in the top of the this depth. Okay, so it is loosely bound because it is just above the, it is just in the top. Okay, so that's why if you give some extra amount like 2.226, then it will this system will separated, that means proton and neutron will be separated from each other. Okay, it is loosely bound. So this Vr is negative V naught, and after R greater than B, the energy is 0. Okay, so according to this condition, we have to solve the Schrodinger equation. So put this value here, then you will get. So before putting, you should know that this psi R, you see there is a vector sign here. This vector sign means the wave function of this deuteron is a function of radial part as well as this harmonic part. Harmonic part is consists of this theta dependence and the phi dependent. That means it is dependent on depends on angular part and as well as that phi part. Okay, it depends on L and this depends on ML. Okay, this depends on L. Theta depends on L and phi depends on ML. Okay, considering the central part, this is central part, not path. Okay, this is central part. Central part means we are considering the central part wave function only, and we are neglecting this harmonic part. Why? Because in the previous number question, that is in the question number 86, I have mentioned that this part, this wave function, radial dependent, the central part wave function has a contribution of 96%. Okay, so that to compare to that 96%, 4% is nothing. Okay, so that's why we neglect this part, this non-central part. This harmonic part is non-central part. Okay, because this is depending on theta and phi. Okay, so and its contribution is 4%. So that's why we neglect it. Okay, we take only the central part. Okay, so if you neglect this theta and phi dependent part, that means the harmonic part, that means what? That means you are considering that your L part, that means there is no angular that means the conservation of angular momentum is present here. Okay, so L equal to 0, that means its corresponding magnetic quantum number ML, it is also 0. Okay, this is the condition for ground state. Okay, and deuteron is only one bound state, single bound state. Okay, if you not understand, you see in the ground state of a deuteron there are two state presents. One is 1d1 and another is 3d1 and another is 3s1. This part has contribution of 96%. Okay, and this part is contributing 4% to the wave function or the potential, you can say. And for this the L value is 2. The L value is 2, and for this the L value is 0. Okay, and you see the ground state of a deuteron is consist of these two parts. These two states are present in the ground state of a deuteron, and here we are neglecting only this 3d1 part. Why? Because its contribution is 4%. Okay, so to make thus our calculation simple, we are neglecting this. Okay, that means L equal to 2 we are neglecting. Okay, and L equal to 0, we are taking the value of L equal to 0. Okay, that means for this 3s1 the L value is 0. You see 3s1, this s, for this s, L equal to 0. So that's I am talking about. Okay, so then what you have to find? You have to put the spherical del operator. This is the del operator in the spherical polar coordinate system. You put this, you must have known this type of expression. You know, use your PG, and this L is the angular momentum. Okay, so it's, you know the value, Okay, L into L plus 1 S square square. So put here, and as we are taking L equal to 0, we are considering this 3D1. We are taking only the 3D1 case. Okay, so then it will this part will be 0. Okay, so only we are getting, only we have only this part. We have only this part, and this part is purely depend on radial part. You see, there are only r expression here, 1 by r square del by del r. There is no theta and phi dependent, because theta and phi dependent part was this only. Okay, and as we are taking L equal to 0, so it will automatically 0. Okay, so for the L equal to 0, this is the ground state. And if you now what you have to do to make our calculation simple, we have to assume that psi r equal to in the expression of another wave function ur by r. Okay, so put this wave function in this expression. Okay, then you calculate. Okay, in this equation, then you calculate, you will get this type of expression. Okay, okay, now what you have to do, put the value of a vr, you know, minus v naught. So if you put minus v naught, you will get minus here, and you can put the value of a binding energy of the neutron. So after getting the value, you see both the value of E, that is the binding energy of a neutron, is minus ED, and VR, the depth of the potential in which the neutron is present, is minus V naught. You have to put with this sign. Okay, take the sign into consideration. Don't put in the only the magnitude. Okay, you have to take the sign, then only you can get this kind of expression. Okay, and as you get this kind of expression where this kappa 1 is this much value. Okay, now you can find the expression of a wave function in the two regions. One region is this inside the potential well, another region is outside the potential well. Okay, and if you are noticing that here I have given a mod mark, mod sign, because this energy of the neutron is negative. Okay, so that's why it is positive here. But if you neglect the, or if you wear out this magnitude sign, then you will get minus ED. So those value, that means I am talking about that, put the negative sign. Okay, take consideration of this negative sign, and according to that you have to put in the Schrodinger equation, then only you can get this expression. Okay, so for this region 1, the value of a wave function is this. Okay, after using all those boundary condition, you will get this. This is for region 1, and for region 2, this is the wave function. Okay, you to take all those conditions, that like for example at r equal to infinity, your wave function should be 0. Okay, these are the basic properties of the wave function. You know, in the like in the case of when you read about the postulates of quantum mechanics, in that case you must have known. Okay, at r equal to infinity, the wave function should be 0, because your particle cannot be spread in the whole universe. It is present in somewhere in a point, or in a space, and that space is not infinite. Okay, so that's why. So those type of conditions you have to put, and you remember that here this gamma has a value of this root over of med by s square. This is the value of gamma. Okay, and here the kappa 1 has the value of this. Okay, so now you have to find the differentiation. So this is the equation of 1, that is the wave function in the region 1, and this equation number 4 is the wave function in the region 2. Okay, so now in the further step we are going to take the differentiation. So take the differentiation of equation 3, then you will get this equation 5, and take the differentiation of equation 4, then you will get the equation 6. Then what we have to find, we have to uh, we have to impose a property like at b equal to r equal to b, both wave functions should be same. Like you see here in this in this in this point, whatever with the wave function, like it is coming in a sine wave, like it is coming like sine wave, and in this after this r equal to b, it is decaying nature. Okay, so at this point, this point, okay, notice this point, at this point the wave function should be continuous. That is the property. Okay, and its first derivative is continuous, and it's a wave function, it's natural wave function, that is a sine kappa 1 kappa r, and this is c e to the power minus gamma, both are equal. Okay, if they are not equal, then that means what, that means they are diverging from each other. Okay, so this should be this is a condition, and there is another condition, the second derivative the first derivative should be continuous. Okay, so after imposing this type of condition, you get these two equations. Okay, these two equations 7 and 8. So what you have to do now, we have to take the ratio. So dividing equation 8 by equation 7, then you will get a minus. You see, I am not you see how this is proceeding. We are getting tan, then if you take the inverse of this, then you will get cot. Okay, okay, you see how this calculation is going. See, so after calculation, after solving this, you will get this. Okay, so it's option A is the correct one. Okay, so option A is the correct one. So option A is the correct one.